Hello, students. I hope everyone's well. We're going to continue on this week with our space unit. Very exciting. We're looking at other space objects this week. I did want to tell you that I would like to next week, so that would be April 22nd. I would like to schedule a Zoom class so I could see all of your faces for once. So I hope that works out for you. We would do it at exactly the same time as our class. So what is that, 11 o'clock? 11:30, right? So yeah, 11:30 on Wednesday next week. We can get together and just, if you have any questions, it won't be for the lecture. I'll go ahead and record the lecture and send that out to you earlier because I like the fact that you can, pause it and stuff like that. So if that works out for everybody, I'll send that information out. If you're unable to make it because you don't have a computer to use, because a sibling's using it, something like that, that's perfectly understandable, and we can work something else out another time. Okay, very good. Here we go. We're looking at other space objects. First, we're going to start off with, we had a question this week. Eliana sent a question via email and asked me if there was something known as the Goldilocks zone. Great question, Eliana. Thank you for asking that. We will, of course, when we talk about some of the planets, we'll get into some of the details about this. But there is something called the Goldilocks zone. We're looking at Goldilocks down there, right? So what was the deal? She tasted the one, and it was too hot, and one was too cold, and then one bowl was just right. Right? So it got to that point. So Goldilocks would be, I'm finding that beautiful middle ground that is just right for something. So in this case, just right of a temperature. Well, we have this in our solar system. It's called the circumstellar habitable zone. How about that? CHZ. That's a lot more big words than Goldilocks right there. But the idea here is that there is a zone around certain stars that make it just right. Let me get a picture up here. Yes, here we go. The habitable zone. Habitable means the ability to live there, to habitate there. So if I have a star that's a certain size, if it's too close, it'll be too hot. If it's too far, it'll be too cold. So I'm telling you, too hot and too cold for what? Well, too hot and too cold for water. Okay, so it's all about water. If it's too hot here, the water will evaporate too quickly. If it's too cold, the water will freeze. But when it's just right, that looks like the Earth right there, huh? When it's just right, the water will be in its liquid form naturally, okay? And that is very important that we have natural liquid form of water. Now, of course, on the Earth, we have water in all three of its phases. We have liquid water, solid water as ice caps and things like that on the poles, and then we have gaseous water, which is the humidity in the air, right? The water vapor that's in the air. And so it's just right, obviously. So we are just right for our position from our sun. Now, take a look at this picture. Not all stars are created equally. We found that out last week, right? Some stars are bigger, some stars are hotter, some are cooler. All right, so if we're looking at a star that's like ours, all right, so it is a, smaller star, an orange star, then the just right zone, the Goldilocks zone, is right here in this green area, which is where the Earth is. Perfect. Mars is just on the edge of it. Venus is too hot. We'll find that out when we look at Venus. But if we have a star that's hotter, it doesn't necessarily need to be bigger, but it's hotter. Look, its habitable zone would be farther out this way. And then furthermore, cooler stars, the habitable zone would be closer in right here. And so do you remember we looked at some of those cooler stars, and some of those are actually larger, right? Just because it's larger doesn't make it hotter. But remember, the white stars were the hottest ones, the blue and white. Then, of course, the red stars are the coolest ones. So the question is, if we have a Goldilocks zone here for our solar system, are there these kind of zones in other solar systems? Well, we've looked into it, and there are some stars out there with some planet-like bodies orbiting them. And the answer is we think so. Yeah, we think that there is a possibility that there could be liquid water on other planets around other suns. Now, these suns are very far away from us. They have to be, right? We can't have suns too close, because then we would have a problem with our sun giving us our Goldilocks zone. Anyway, so great question, Eliana. I hope that answered it for you. And anybody else, if you have questions, I'd love to address those. And then next week when we get together for Zoom, if you have them written down, we can answer them then. You can kind of see if you can stump me on some stuff, okay? Great. Let's move on to the other space objects. We're going to start with asteroids. If you see that word aster, do you know what that means? That actually means star. So this is like little star. It's not a star. It's something else. Let's find out what it is. They are irregularly shaped pieces of rock, metal, and dust that are floating around out there in space. All right? And sometimes they will start to move throughout space. Most are small, about the size of a pebble, so not huge. Some are huge, called minor planets. So if they're really big, and we'll look at some of the minor planets. In fact, you already know one of the minor planets. It's called Pluto, right? It used to be actual planet, but now it's been delegated, sadly, in my opinion, to a minor planet. Okay. Where are they? Where are these asteroids? Well, it turns out a large number of them are between Mars and Jupiter. So here's Jupiter, here's Mars, and there's this thing called the asteroid belt, or the main asteroid belt. And that's because there are other asteroids. In fact, there's a really large one way, way out called the Kuiper belt. We'll get to that, because a lot of those end up being frozen, and they'll actually not be asteroids anymore. And then there's this other thing called the Oort cloud, O-O-R-T, Oort cloud, which we have theorized is out there. We haven't ever seen it, but it's a giant surrounding of, we think, frozen rocks and things like that. All right, so the main asteroid belt we're going to find out that Mercury, Venus, Earth, and Mars are called terrestrial planets. That means they're planets with solid ground. And then outside, Jupiter and the ones beyond it, Saturn, Uranus, Neptune, are not terrestrial planets. They're gaseous, sometimes called the great gas giants and things like this. So what in the world is this asteroid belt right here? Well, there's been a lot of wondering about that. Notice that there's some asteroids here. It says Trojan steroids right here. Some of these end up being asteroids. Some of these end up being moons of Jupiter, actually. And so we're going to see here. Here it is. Is it possible that the asteroids in this belt are remnants of an old planet that exploded? So the idea here is that there was a planet that was influenced by something that caused it to dissipate and explode. And that thing would have been Jupiter, actually. It would have been, Jupiter's massive. It's our largest planet in our solar system. And it is so big that it has a really, really strong gravitational pull. And it could have caused that. But more thinking is now in the area that this debris it was debris that could have become a planet. All right, so in other words, instead of exploding, it just never formed, and the reason it never formed was because of the gravity of Jupiter. The bottom line is we're not sure what it caused the asteroid belt, but these interesting theories are fun to think about and wonder about. So we're not exactly sure. The largest known asteroid is called, some people pronounce it Ceres, some people pronounce it, we'll see in the video, I think I pronounce it a little different. Ceres, maybe. Look at it. It's pretty round, isn't it? In fact, it's the roundest one, I think, that we've found. Look at all of those craters on there, like our moon, right? Lots of craters. We'll talk about craters here. In fact, our lab will be about craters today. It's actually a pretty fun little lab. So we'll take a look at those a little more closely. It is in the asteroid belt, in the main asteroid belt, orbiting around there. In fact, let's watch our video, because we're going to talk about the guys who first saw it and wondered about it. Oh, this one, 2014 JO25, it actually made a close flyby of the Earth in 2017. At its closest approach, it was 1.1 million miles away from Earth. But we could see it, and there it is. That's actually a video that we took of it. It's repeating there. We took that video of it as it was flying by. I don't remember this. I don't know if anybody tried to make us nervous about an asteroid headed toward Earth, but it was 1.1 million miles away, which is still considered pretty close astronomically. So here we're going to look at some of the types of asteroids that are out there. Okay, we have the vast majority are this type right here. All right, notice both of those are in this right here. Okay, so we're going to see this types C and D, And then we have X and S. S is really strange, yeah. So this one is metallic. Which one is that pointing to? Iron, pointing this way. Okay. Yeah, this is a little confusing right here. And where they may have come from, rubble pile, internal heating, this kind of thing. Most of them are like a rock, and then some of them have metal associated with them. Those are the two most common types. And let's watch. Well, no, that's not the video yet. Okay, here's a picture of some of them. We've actually got some photography of some of them that are out there in the main asteroid belt right here. So we see Matilda and Ida, so somebody maybe named those after loved ones, I'm not sure. Eros, that would be a goddess or god of the ancient Greeks. Oh, interesting, this one's called Anne Frank. Okay. And Braille, yeah, probably named after famous people. Here's Halley. Halley was a famous astronomer who named the comet, right? Halley's Comet, which we'll get to soon. All right, here's our video. This will explain some of those types to us.
What's inside the asteroid belt? Out in the cosmos, between Mars and Jupiter, lies the asteroid belt, where various large chunks of rock are floating in a disk and orbiting the Sun. It's a standout feature in our solar system, but is there more to it than simply miles and miles of random, well, asteroids? You bet there is. Back in the mid-18th century, the German astronomer Johann Titius worked on the Titius-Bode law hypothesis, in which it suggested that each planet in the solar system was twice as far away from the Sun as the preceding planet, making Venus twice as far away as Mercury, Earth twice as far as Venus, and so on. Regardless of the accuracies or inaccuracies of this theory, in 1766, Titius correctly applied it to assume that there must be a celestial object 2.8 astronomical units away from the Sun between Mars and Jupiter. Fast forward to 1801, and Giuseppe Piazzi, a Catholic priest, discovers such an object moving against the distant stars. Piazzi originally thought and hoped it was a new planet, but he officially announced it as a comet, not wanting to disappoint the world should he be wrong. Mathematician and physicist Carl Friedrich Gauss then studied the mysterious object's orbit and ultimately proved Piazzi correct. He had indeed discovered a small planet, and it was exactly where the Titius-Bode law predicted that it should be. This planet was swiftly named Ceres Ferdinandia after the Roman goddess, and King Ferdinand IV of Naples and Sicily. Of course, the Ferdinandia part of its name was eventually ditched, and plain old Ceres is today classified as a dwarf planet, but the discovery sparked a slew of similar finds. The following year, a second body was identified, 2 Pallas. This massive asteroid actually accounts for 7% of the total mass of the entire asteroid belt. So as far as space rocks go, 2 Pallas is a stonker. Then by 1807, 2 further small planets were discovered. So that's 4 new celestial neighbors showing up in our skies within 6 years. Naturally, scientists at the time were seriously excited. Next came a brief pause for the Napoleonic Wars, but afterwards even more space-based bodies were found. So much so that by 1850, our knowledge had expanded enough to understand that not all of these sightings so close to one another could be genuine planets. In fact, none of them were. Struck off the official planets list, they became known as asteroids instead, and were grouped within the asteroid belt. By 1868, 67 years after the first was discovered, over 100 asteroids had been found. Almost a century and a half later, by the year 2000, we'd officially charted 100,000 of them. And while there's no official and conclusive number today, there are potentially millions of asteroids floating between Mars and Jupiter. Ironically, the Titius-Bode law that started it all off has since been discredited as being total nonsense, and Piazzi's initial discovery of Ceres has been labelled as little more than lucky. But both developments clearly prompted a significant change in how we understood the solar system. So we know there are millions of these things out there, but what exactly is an asteroid? Simplistically speaking, it's a space rock. Some of these rocks, like Ceres, which has a diameter of 945 kilometers and accounts for an incredible 33% of the belt's total mass, are massive. Others are tiny, reaching less than 10 meters across. It's a common misconception that all asteroids are huge, but it's just not the case. In fact, if you could somehow collect every asteroid in the asteroid belt and fuse them together by gravity, forming one massive asteroid planet, that planet would still weigh less than the Earth's moon. Similarly, for years Hollywood movies have had us picturing the asteroid belt as a massive and intimidating wall of impenetrable rocks destined to destroy any passing spaceship. But that's just Hollywood being Hollywood. In reality, the chances of actually hitting an asteroid while passing through the belt are less than 1 in a billion. Yes, there are millions of asteroids, but space is so unbelievably vast that they're all extremely far away from each other. As for their composition, asteroids are made up of various materials and are separated, for the most part, into 3 classifications. The most common type of asteroid is a C-type, or carbonaceous asteroid. These account for 75% of all of them, consist primarily of silicate rock and clay, and appear grey in colour. The second most common is the S-type, or siliceous asteroid. These are a greenish red and are made of nickel, iron, and silicate. Finally, the rarest major type of asteroid is the M-type, or metallic asteroid. These are fully red and are composed primarily of nickel iron. There are other, even rarer types out there, like the V-type, which is made of volcanic crust, but C, S, and M are the major players. But what's in the belt itself? What brings all of these asteroids together, and why haven't they relocated yet? As with many things, it's all down to Jupiter. When the solar system was forming over 4.5 billion years ago, in a well-known creation story, massive clouds of dust and rock were brought together under the force of gravity to form the planets. But Jupiter grew to be so massive that its gravity directly influenced the way in which nearby rocks moved too, preventing those close by from coalescing into fully fledged worlds. While some collided every now and then, and some were snagged to eventually become one of Jupiter's many moons, the majority were kept at a constant distance away from the gas giant, and so they formed the belt. Were it not for Jupiter, it's entirely possible that the rocks in the asteroid belt could have created another new planet, or else attached themselves to existing planets like Mars. But Jupiter's gravity overpowered their own and prevented them from uniting. This way, Jupiter also protects us here on Earth from constant asteroid bombardment. Given that Jupiter's gravitational pull keeps all of the asteroids in the same place most of the time, the space rocks careening through the solar system are few and far between. But of course, even with Jupiter, there are asteroids outside of the belt. Scientists believe that Mars's moons, Phobos and Deimos, started life this way, and there have been at least 18,000 near-Earth asteroids throughout history, some coming closer than others. But back to the belt, and it's true that some of the rocks that reside there, while affected by Jupiter, are massive enough to exert their own gravitational pull. In the case of Ceres, it's actually the only asteroid to be completely rounded by its own gravity, which only increases its planet-like properties. Elsewhere though, over 150 asteroid belt asteroids boast a companion moon, and scientists have even discovered binary or triple asteroids where 2 or 3 are locked in a gravitational orbit around each other. So, all things considered, the asteroid belt is very far from just a random assortment of space rock. It's more like a well-balanced, carefully shaped and continuously working machine, with asteroids orbiting other asteroids orbiting the Sun. There are a few dwarf planets in there, amongst millions of other bodies, each as unique as the last. But the belt could perhaps be best described as a place where another planet might have formed, had the solar system been structured differently.
All right, so interesting stuff there. A lot of that is theoretical, of course, as far as formation and that kind of thing. But interesting to think about. Definitely the gravity of Jupiter has something to do with it. And I think it's interesting that the moons of Mars, which we'll learn about in a future lecture, may be some of those asteroids. I never really thought of it that way before. So interesting there. All right, so there are asteroids in the belt, of course. Some of them will fall out now and then, but mostly they're staying there in their orbit. There are also other space rocks that become asteroids as well. Which brings us to this when they start to come closer to us, right? So a meteoroid is a little different. It is a chunk of metal or stone, possibly an asteroid, right, that starts moving toward the Earth's atmosphere. These are the ones that are going to be falling out of the asteroid belt or coming from another location, wherever that might be. They're called meteoroids when they're headed our way. If the meteoroid reaches the atmosphere, it begins to heat it up from friction. You know, the air is going to heat it up really well. And then it will be known as a meteor. We will see these frequently as a shooting star. Okay, so we will find out that oftentimes when we look at meteor showers, we'll find out where they're coming from pretty soon. If a meteor actually hits the surface of the Earth, if it's big enough to not be completely burned up on the process of entry, then it will hit the Earth, make a crater in the Earth, and known as a meteorite at that point. Large meteorites can leave a giant crater on the surface of the Earth. So what's it called? When it's in space, careening, it's called a meteoroid, headed our way. When it enters into our atmosphere, it's called a meteor. So you've probably heard of a meteor shower. And then when it hits the ground, it's called a meteorite. That'd be a good Jeopardy question, right? And we'll watch a video about it.
This is our solar system. Because the sun's gravity is so strong, nearly everything is settled into similar orbits. We call this the orbital plane. Most maps of the solar system just show the planets, but there are a lot of objects flying around in space. This is the asteroid belt, roughly between Mars and Jupiter. Beyond Neptune is the Kuiper belt, and out here is the Oort cloud. There are also lots of stuff that doesn't fit neatly into any of these categories. The smaller you get, the more of it there is. All of these space objects are flying around and sometimes colliding with Earth. When these objects hit Earth, they burn up in the atmosphere, creating brilliant streaks of light. This is what causes shooting stars. However, did you know that most shooting stars are not spaceship-sized rocks hitting Earth's atmosphere? Most shooting stars are actually just little specks of dust, and most of the dust comes from comets. Comets come from the most distant reaches of our solar system, where the sun's gravity barely hangs on. This lovely location is called the Oort cloud. Scientists have never actually seen the Oort cloud because it's light years away and very dark. But based off the unique orbits of comets, they hypothesize that there must be a massive cloud of icy and rocky material with millions of comets surrounding our solar system in a giant sphere. Because comets that do make it into our solar system come from so far away, they orbit our sun differently than any other body in the solar system. Rather than staying on the same orbital plane as most of the planets and everything else, comets orbit in tight ellipses tilted at amazing variations from the orbital plane. Orbital shapes are described in terms of eccentricity. An almost perfect circular orbit, like Venus follows, has an eccentricity of almost 0. On the other end of the spectrum, the famous comet Hale-Bopp, which passed the Earth in 1997, has an eccentricity of nearly 1, which is about as eccentric as you can get without getting flung out of the solar system forever. Because they have such eccentric orbits and come from so far away, some comets take hundreds to millions of years to orbit the sun. For example, we won't be seeing Hale-Bopp again until the year 4380. Up close, a comet is just a pile of extremely dark, dusty rocks, held together by frozen gases and water. As a comet's orbit takes it closer to the sun, it transforms into something far more beautiful. The sun warms the frozen ice of the comet. The heat causes the ice to melt, or rather, sublimate. This means the ice skips the liquid phase and goes straight from solid into gas. The increasing pressure from the expanding gas trapped in the comet creates mini explosions on the surface. These mini explosions release gas along with chunks of rock, ice, and space dust. The gas forms a cloud that surrounds the comet called a coma. And as this gas and dust gets pushed farther away from the comet by solar winds, it forms a long, beautiful tail that can extend for millions of miles away from the sun. The light we see isn't emitted from the comet. Rather, we see the light of the sun reflected in all that gas, dust, and ice. The larger particles ejected from the comet continue in roughly the same orbit. This is called the dust trail, or meteoroid stream. After making multiple passes into the sun, completing the same orbit again and again and again, the comet has ejected enough space dust to form a complete meteoroid stream. This debris fills the orbit of the comet. Imagine if someone paces around your kitchen table, eating cookies following the same path each time. Eventually, there will be a complete ring of cookie crumbs left behind. This is essentially what a meteoroid stream is, a giant ring of space crumb debris, or future shooting stars. Each year, when Earth passes through this meteoroid stream, we intercept all of the specks of dust and rock left behind, and a meteor shower is the result. So even hundreds of years after a comet has passed through our solar system, the Earth can continue to enjoy a meteor shower every year around the same time when we pass through the comet's old orbit. So next time you witness a meteor shower, tell your friends it's more like a dust shower. Thank you so much for watching. Subscribe for our next video.
Okay, so that we'll talk about comets here a little more with a little more detail, but that had a really good introduction to it. So think about it as the meteoroids, are going to be out in an asteroid area, so it'll be rocky, or coming from a comet's debris that was left behind. All right, so very cool. This is a giant crater that was formed by an asteroid a meteorite that was found right down. It's huge. I don't know if you can tell. There's a building down there. These are cars in a parking lot, and here is a facility. They've been out here. This is in the desert, I believe, of Arizona, where we can still see it, right? So we've had other craters formed on the surface of the Earth. It's just in most places, erosion has taken care of them. Most of them aren't this large, of course. They'd be smaller. The vast majority of meteorites do burn up in the atmosphere and never hit the ground, right? So when they do, we can study them. So in fact, there would have been a meteorite at the bottom of this crater, which I assume that they found, and were able to study it. Typically, the ones that make it through are the ones that are made of metal. And the metal ones tend to survive, right? Because that makes sense, doesn't it? The rocky ones tend to break up and burn up on their way in. Not that they never make it, but the metal ones tend to actually make it to the ground. So this is another crater right here that's been filled with water. So it's just in an area that's a little more wet, left a crater behind. Very cool. Which brings us now to our comets. I love comets. I think they're fascinating. We'll talk about the famous Halley's Comet here in just a second. So what is the comet? Well, it is a chunk with frozen gases on it. So water and dust, things like this. So we call it a dirty snowball. It's kind of like a snowball coming through space. It came from farther out than the asteroid belt, because the asteroid belt, typically those are the rocky ones. So it came out probably from the Kuiper belt, which is beyond and actually Pluto is in the Kuiper belt. And then beyond there, this mysterious thing called the Oort cloud. And depending on if they are, there's some comets that have a short span and some have very long. We'll see a video here in a minute to give us a little more information on comets. But as it's coming toward the sun, we can see this tail coming out from it. Okay, so it is a frozen snowball here, something in the middle, some sort of rocky thing, and this frozen part right here, the icy part. And as it comes toward the sun, actually the sun's energy, so the solar rays that are coming off of there, called the solar wind, is blowing against it, if you will. So the sun's pulling it because of the gravity. And as it does that, it starts to, did you hear the word sublimate? Sublimate, so it goes from its icy solid straight into a gas. So do you remember, I believe with your class, didn't I bring in some dry ice one time? And we were looking at the dry ice and saw how it just turned from a solid. If it's not this class, if I'm remembering wrong, you've probably seen dry ice. It's a solid, and then it just turns into like the smoky gas, right? It doesn't go through a liquid phase. If you put it in some water, it'll bubble through there and release the gas. That is sublimation. And frozen CO2 does that. It just doesn't go through a liquid phase here on the Earth from there. That's what's happening with these comets. So it's going straight into that gas. Okay, so some of it's falling apart. So think if it's a dirty snowball, that means it's got the ice and then some other stuff in there, some, rocky dust and that kind of thing. So the dust tail will come off like this, All right, you can see it right here. This is a fabulous picture if it's real. So the dust cloud here, and then what was called the ion tail, the plasma tail. And the video mentioned that this is only visible because of the reflection of the light from the sun coming from it. Okay? And furthermore, that the tail always faces away from the sun, depending on where it is, right? So the tail will be going away because the sun, think of it as a wind blowing it, you know, rather than the tail is not really part of the comet so much as it's part of the result of the wind blowing against it, the solar wind blowing against it. So this dust tail right here is what's going to leave that debris in that orbital area that when the Earth passes through it, we end up with our meteor showers. So one of the most famous meteor showers happens in August, about August 10th or so. It's called the Pleiades, and the Pleiades is, the reason it's called that is because there is a constellation over there called the Pleiades. I think I showed it to you last week. And it looks like it's coming from that direction. Okay, it's not. It's the orbital of the ancient comet. But as we pass through it, we get lots and lots of those meteor showers. Very, very cool. All right, we're going to watch a little video here on comets, okay? And this will give us a little more information. It's going to furthermore talk a little bit about Edmund Halley. You may have heard him called Halley's Comet, but I think typically people like to call it Halley's Comet. It was here in 1986. So I was around. My daughter actually was born that year, and so she was born in the year of Halley's Comet. We had to have a picture of it, and it wasn't very impressive. We weren't on the near side of the orbit at that time, sadly. Sometimes it'll look massively huge in the sky. In fact, some of the famous sightings of it, I think this video will talk about it. It was very, very large in the sky, and where people were frightened, you know, thinking the gods were, you know, angry or something like that. So let's watch and see.
Born in the dark outer reaches of our solar system, comets are lonely wanderers. For thousands of years, comets have drawn the attention of philosophers and astronomers. Many ancient peoples from cultures all over the world believed that comets were a sign, either of good fortune or disaster. Comets were thought to be fireballs or hairy stars traveling through the upper atmosphere. That is where they got their name. The word comet comes from a Greek word meaning wearing long hair, referring to their long, bright tails. It was Isaac Newton who described comets as solid bodies with thin tails of vapor heated by the sun, a description supported by modern astronomical observations. Comets are similar to asteroids, but unlike asteroids, which are mostly rock and metal with small amounts of ice, comets are made of ice, dust, and frozen gases. Because of this, comets are often called dirty snowballs. While out in deep space, they are unremarkable lumps of ice and rock, but as they enter the inner solar system and come closer to the sun, they begin to heat up. The comet's ice begins to sublimate, or turn directly into gas. This gas creates a cloud around the comet, making it seem fuzzy. There are three main parts of a comet: the nucleus, or solid central structure made of rock, dust, and ice; the coma, or dust and gas forming a thin atmosphere around the nucleus; and the tails. Comets generally have two different tails. One is made of gases, the other is made of dust. These two tails usually point in different directions. The gas tail is blown directly away from the sun by the solar wind. No matter which way the comet is traveling, this gas tail will be pointing away from the sun. The second tail is made of the dust released by the comet. The dust tail usually points back along the comet's path. A comet's tail may stretch as far as 6 million miles or 10 million kilometers long. The orbit of a comet is usually elliptical or oval in shape and may have a length of only a few years or as many as millions of years. Comets may be classified by the length of their orbits. Periodic or short-period comets are comets that orbit the sun in less than 200 years. Comets with orbits of 200 years to 1,000 years in length are called long-term comets, and comets that take more than 1,000 years to orbit the Sun are called near-parabolic comets. Some comets, called hyperbolic comets, pass by only once and then exit the solar system. Comets that pass extremely close to the Sun are called sun-grazing comets. Some large sun grazers survive to go around the Sun over and over again. Other comets travel so close to the Sun that they evaporate or break into fragments and are destroyed. Comets are believed to come from two places on the outskirts of the solar system: the Kuiper Belt, a region past Neptune filled with asteroids, dwarf planets, comets, and more, and the Oort cloud, a sphere of icy leftovers from the creation of the solar system, nearly a light year away from the Sun. Scientists believe that short-period comets come from the Kuiper Belt, and long-period comets come from the Oort cloud. Because these comets are made of ancient material and come from so far away, astronomers love to study them as they come near. In the past, comets could only be studied through ground-based telescopes, but over the last 30 years, spacecraft and probes have been used to visit and observe comets. In 2014, the European Space Agency's Rosetta space probe successfully landed on the surface of a comet, the first time this had ever been accomplished. Still, even seen from Earth, comets can be spectacular to behold. Probably the most famous comet in history is Halley's Comet. Halley's Comet is named after Edmund Halley, who realized that the three bright comets seen in 1531, 1607, and 1682 were actually the same comet returning over and over, and successfully predicted that it would be seen again in 1759. Halley's Comet comes back every 75 years and last appeared in 1986, meaning it won't return until 2061. In the meantime, comets that are visible to the naked eye pass close enough to see from Earth roughly once a year, although not many of them are bright enough that they are easy to see. If you see something that looks like a fuzzy star with a trailing tail that is visible for a few nights in a row, you're probably looking at a comet. I hope you enjoyed learning about comets today.
All right, there we go. So that had some repetition, but also just that different information about, where they are coming from, the short-term ones and the long-term ones. So like it was mentioned there that the tail points away from the Sun. Notice the blue tail would be the gas tail when we talked about plasma, that kind of thing. And so, but notice they're pointing away, away, and away. Yeah. So when it looks like it's going backwards right here, but it's really just because it's going to point away. When it gets all the way out here, of course, it won't have the tail anymore because it'll be far enough away from the Sun to not be influenced by that solar wind anymore. So this is just like a wrap up of the different things. I thought it was really cute. There's animation in here that's kind of fun. So let's watch this one.
Space rocks. Our solar system is a vast and fascinating place. Between Mars and Jupiter, we find the asteroid belt. Due to the mighty gravitational effects of Jupiter, these chunks of rock and metal couldn't come together to form a planet, and instead made up a solar junkyard of sorts. This is a crowded place to be an asteroid. Sometimes they collide with each other and get knocked off course, and even out of the belt altogether on a very different journey through the solar system. There are lots of names associated with space rocks, so what's the difference? Well, the bigger rocks are called asteroids. The smaller are meteoroids. And when they fly through the Earth's atmosphere, they are called meteors. If they manage to survive their burning descent through our atmosphere and land on Earth, we call them meteorites. Some meteorites contain iron, which makes them very dense, dark, and magnetic. They are the oldest thing you could ever touch, as they are the same age as the solar system. The gas giant Jupiter marks a boundary in the solar system called the snowline, beyond which objects contain a lot of ice. Past the other three gas giants, we find a huge ring of ice chunks large and small called the Kuiper Belt, where the dwarf planet Pluto lives. Even more of these ancient, dirty snowballs exist in a huge bubble called the Oort cloud. These icy objects can get bumped off course sometimes to become comets that journey past the planets towards the sun. Some collide with other objects and get smashed to bits. Others head towards the sun and form long, beautiful tails as their icy surfaces warm up. Here they will either fall into the sun, never to be seen again, or they will survive and speed back home beyond the snow line. Here on Earth, we are treated to spectacular natural firework displays in the sky from orbiting comets. As they get close to the sun, they burp, splutter, and crumble, leaving behind a trail of debris. At certain times of the year, the Earth plows through these trails and bits of comet flare up as they fly through our sky and become meteors. The early Earth was hit by thousands.
All right, so I just like the animation on that one and just kind of reviewing the stuff we talked about right there. Okay, which brings us to, I thought I had a picture of a meteorite to show you there. They kind of like a softened up metal looking thing. All right, so this lab is in your book. It's actually quite a bit of fun. What I have on the right over here is a little tub of flour. Interestingly, flour was kind of difficult to locate. Yeah, so it wasn't on the shelves at the grocery store. Apparently everybody decided to start baking while they're home. So I used my last bit of flour. I would have had it in a larger tub if I had more flour. So I put it in kind of a smaller tub because it's all I had. All right, so the flour's in the tub. And then I'm covering it. That spoon right there is some cocoa that I'm putting over the top. And the reason we do that is to show a nice layer there of the cocoa so we can see when we drop the ball in here. And now that I look at it, I probably could have used more cocoa in there. We have 3 balls here on the left. Now I've weighed all of them. You can see them all on their scale right there. And what I have is a very lightweight ball. It's a ping pong ball, only 9.65 grams. One approximately the same size as the ping pong ball, but look at the weight. Wow, quite a bit more, 59.61, right? So there we go, lots heavier, but about the same size. So we're going to look at size and weight here. Then I have a tiny metal ball, pretty small, but look, it weighs 8 grams, almost 9 grams. So it's fairly heavy for that. So we're going to be looking at 2 different things here. When we drop the balls down into the flour, we're going to be looking for the mass of it, and also the size of it, okay, to see if they're going to make little craters in our flour. So this is also, if your mom is willing to let you have some of this hard to find flour, you could try something like this at home as well. You may not be able to have a scale to weigh them, and that's okay. Just get a general idea of the lighter weight one and the heavier one, the little balls you're going to drop in there. In fact, you could drop in other things like a little rock if you wanted to. It doesn't have to be a ball. Okay, so I have a little video here in just a minute, but it was hard to videotape all of this, so I'll show you. Now I did figure out finally how to make my videos longer with using my phone, so hooray. But at this point I didn't know that yet. So I have the little metal ball here, and I'm going to drop it, and you can see I'm holding that at 20 centimeters, and so I'll put that over the flour, and I'll drop it in. There it is. So it dropped in and made that little crater right there. All right, then I stuck this stick down in there to get a measurement. You're going to see here, I measured how far it went down. So from here to here, and what is that, about 5 centimeters or something like that. We'll see on our little data sheet here in just a minute. All right, so that was the first one I put in there, and that was at 20, dropping it from 20, and it went that far down. Then I dropped it from 60, I think, and it went all the way down to, it looks like 9, so I dropped it again, and then I dropped it a third time from the whole meter stick, okay? And it actually went all the way to the bottom of this little tin right here. So it hit the bottom. So our data was limited by my pan, which I think it got down to, we'll see what data I put on there, was either 13 or 14, something like that. Okay, so that was the first ball, the little metal ball. And then I was going to try the other ball. So here is the ping pong ball. Here it shows me on the left dropping it from, I guess, 20 centimeters. Then I did 60, and then I did the full thing. The funny thing about this one is, look over here. Right here you can kind of see where the ping pong ball hit. It kind of made a little interesting divot right there. And then you can't even see the other one, somewhere around here, okay? So it didn't make a very massive impression. Remember, it's lightweight. And furthermore, with its size, it's sort of spread out. It's falling there, right? So it spreads that out a little bit. So I have the data for that. It didn't make much of an impression at all. Then we're going to try the large ball, the large funny color ball. And this is our video right here. Let's see what happens on this one.
Offers within 72 hours.
For the end here, so we're going to go at 20. We're going to start at 20. How deep do you think it'll be? Goodness gracious, here we go. Wasting time. 20. All right, that deep. And now we'll go 60. I gotta hurry. 60 this high. Wow, and then we'll try 100. All right. Okay, do you see the difference in the craters right there? Okay, very good. Hopefully it didn't go too long. For the okay, so my phone was, and I'm sorry about that background information. I mean, it's noise. It must have been a radio or something playing. So I really felt rushed doing this. So sorry about that. I also noticed. Did you see how I sort of lifted the meter stick? I didn't realize I was even doing that, but that may have made those a little farther than I thought. Furthermore, I don't know why I didn't think of it to take a picture of it afterwards to show all of those depths right here. So let's see if I can find, and maybe, did I get it? There it is right there. So you can see, so was this the deepest one? Yeah, see, I think the ball's still in there, right? So it was this level, then this level, then this level. I should have put more cocoa on there as well. All right. Okay, so on page 167 of your lab book, we have the spot to record this data. And like I said, if you want to try something like this at home using your own stuff, you're welcome to do that. If you do, take a picture, send it along to me. You get extra credit for that. So I put down what I was dropping. All right, the ball's right here. The masses of those right there. And then I did the experiment. So my depth at 20 centimeters for the metal ball was about 5 centimeters. And at 60 centimeters, my depth was about 9. And at 100, it was about 14. All right, so I definitely gave it that little extra right there. Okay, so I'm just going to write these down real quick. 5, 9, and 14. All right, good. So then our next ball, the ping pong ball, which didn't go very far at all, it was like about 1, and then a 1, and almost like 1.5, and not even 2. You see, so its crater, didn't have much of a difference. So there would be, it was fairly large, but its mass was not great. Okay. Then our heavy ball that was that same size there, it's going to be a little better, right? So it went down about 3 centimeters, and at 20, and about 5, and then about 8. Okay. So that's interesting between the heavy ball and the metal ball. So remember, the mass of the metal ball was different. It was only 8 grams, but it was compacted into that small area, right? Into that metal area. So notice how, and keep in mind, remember at this data point right here, it hit the bottom of the pan. If I'd had a bigger pan, I would have maybe had a more accurate deal on that. If we had all been together, I would have had a tub that was, and we would probably had about 2 groups trying this. And we might have been able to get all this data, or maybe not. Okay, so in your book, you're going to make a record. If you want to use my numbers, then you can use my numbers. That's fine. If you want to do your own lab and then have your own data numbers, then go ahead, go for that too. So on page 168, you're going to see this really great graph over here. So on the left, it says depth in centimeters. You're going to write centimeters over there. And on the bottom, it's going to say height dropped in centimeters. So on our metal ball, what you'll do, for instance, is from 20 centimeters, we have to figure out what these represent. So what's it? 1, 2, 3, 4, 5. So that would be 10, 20. Okay, so we can do 5, 10, 15, 20. We can count these 2, 4, 6, 8, 10, 20, 30, 40. That's still not enough. So we need to be able to get to 100, right? So if this is 100, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Maybe y'all can figure out a better counting than I did. But at 20, we were only at 5, right? So this was for the metal ball. So what you do, for each ball, use a different color of ink, and you can put them on here. So we'd be at 20. Let's say 20 is about here. And then we were at about, so at 20 we were at 5. And at 60 we were about 9. Sorry, my thing keeps going away. 5 and 9. And then 14, I'm almost going to make like a line that goes like this. But our other data is going to make the lines a little different. Okay, so then you'll end up with this cool graph thing showing essentially that the impact is greater when it comes, from a greater distance, that kind of thing, and a greater mass, or that mass in that small metal ball kind of a thing. Okay, but it's great often for scientists to plot their data onto a graph, because a graph you can just get a snapshot. You look at it and get an idea of what happened with the experiment. All right, so that is it for today, y'all, with our craters. So I hope you enjoyed that. Remember, next week I will send your lecture probably on Monday or Tuesday, and then I will try to do our Zoom class on Wednesday at our regular class time. Okay, everybody have a great week. Bye.